Okay, here we go. Just what I added, which is now here, and I guess I looked at. Sorry, second hour. Someone sitting right there asked me a question about the homework, um, about a density curve, and then it asked something. The very first one, a little confusing. So I'll actually cover that after I go over this. These are little histograms. And we could call this probability histograms, which we did actually do, where the bars represented some sort of probability up here. Um, and this maybe went up to zero point 0.3. So that means, this is 30% of the day. I don't know if that's going to work out, but that's what that means. That bar's at the zero point 0.3 height, so that's 30% of the data. Then all of these represent less than that. But it's supposed to add up to what? What did the percentages add up to become? 100. So I'm probably off on that. I'm just giving you an idea what the height of the bar actually means. And then these represent data points on the x-axis. Well, what we could do is turn this into a curve. And then, like in calculus, I know they talk a lot about area under a curve kind of situation. So take these histograms, then we can actually put a curve, and then we could use the boxes to estimate the area under that curve. Because finding the area of rectangles is very simple, right? Length times width, right? And then let's finish off these notes and talk about that number 1 in the book. And then this is a calculus idea. Remember doing this in pre-calc. There's a little chapter 10 intro to calculus section. I don't think we did it last year, though, for the CAT students. But anyway, let's finish this off.
So are those histograms opposite what they were before with the mean and median? Like when the mean was smaller, it would get.
I just pressed play. I wish they could have heard that. Okay, this is, I didn't put this up before, but if you put the data points on the x-axis, this is where the mean would be, like on the, I'm just making this up. But it would be right of the median. That's where this term comes from. True. In relation to that statement there. Okay, now, non-normal. All right. So what's a normal distribution? A normal distribution is one that is symmetric. Okay. Well, that's not. Let's put it this way. A normal distribution is symmetric. Doesn't mean if it's symmetric, is it normal? That's not. It's not true in the reverse. So non-normal distribution is definitely not symmetric and doesn't hold the percentages that I'm going to show you coming up here. Okay, so we use these curves, and the area under the curve is always equal to 1 because the area under the curve actually represents the percentage of something that is likely to occur. So, all those percentages, it can't be more than 100% for a certain scenario. And I'm kind of gumming that up a little bit. So let me go to the first example and clarify that. The density curve shows the distribution of time men spend on the phone in a week. Well, if you survey 1,000 men, that's it. That's 100% of the men that you surveyed. And you got answers all the way from 0 to answers possibly above 320. But no matter what, 100% of the data is you either went from 0 to, I don't know what the highest amount is. That represents 100% of the data. And then what does this mean right here? 18% of the guys at least spoke, they spoke up to 150 minutes on the phone. That's what that number means. And it's expressed as an area. So that yellow is supposed to be 18% of all of this area. That's what it's supposed to happen. It's hard to actually graph that and make it look nice. So anyway. Hey, is there something missing, by the way? Is there something missing? Which one's missing? Is anyone in this class? I'm teaching a bunch of ghosts.
I don't know, or I would have answered it.
Is there a value missing in these sections?
Yes.
Yes. What should that value be, or what should it actually make sure happens? that all the percentages or decimals. Oh, I just lost my sneeze. That's so frustrating. Equals 100. Okay, so 30, 50, 68, 76, 24. This should be a 24 here. So that was missing on purpose, just to get you to understand that, 100% of the data falls underneath this curve. 100% of the people that we asked are in this, no matter what their values were. And then I just shoved the answer in there because this is Mickey Mouse. Do you remember this, by the way? Yeah, this is a Math 2 thing, I think, right? So rejoice in Chapter 11, although, it'll ratchet up a little bit, but I think Chapter 11 is 100% review. All right. 54% fall within that. I colored those in yellow, right? Okay, and then I'll pause. A very simple day. All right. Now try to do this. Normal distribution is not only just symmetric. There's more. Okay, normal distribution has the following, and then the next page. But the first thing I'm going to do is break this down, what happens here. First of all, what's this value on the bottom? Everyone all day long got this right. Mean. Now, it could be one of two things. It could be X bar. What's that the mean for? Mean of a sample. And it, it really depends on what you got to kind of analyze that as we go. Or it's going to be given to you. This is a sample. This is a population. Whereas mu, I should ask you this, is a population mean. I should have put mean population, keep that same as up there. But so I don't care what we do. On the next page, I change them all to means. So, I'm sorry, mu's. So that is mu, the population mean. And then when I go here and here, what did I call these on my Algebra 2 notes back in the day? I said this was this and this, right and left. What am I looking for? Again, all day long, first and second, got this right away. What? One deviation to the left and one deviation to the right. And then that's the last time I'm going to write something up above here. So how does that look as a variable? I do have a problem with my Algebra 2 notes, and I'll show you on the page next. If I'm dealing with mu, then this symbol, lowercase sigma, I come to find out, right? That is standard deviation of a population. Whereas S is standard deviation letter for a sample. Okay? All right. So this would be mu minus, using the correct variables, should be, as far as I understand, as someone that's smarter than I at statistics or knows more about it may come by and say, you're wrong, idiots. But that's what I've seen with this book. So then this would be mu plus 2 deviations. Then approximately mu plus 3. Mu minus 2, and that's fine, I'm going slow. That lets the note takers catch up. Mu minus 3 deviations. Okay, now pause this for a second. Plus 5. Now they have a firmer understanding after teaching this 1 year. The next thing, I think, it's definitely an approximation. Remember, statistics are not perfect. They try to make predictions about stuff, and they're roughly we could expect this to happen. So the empirical rule, I think, is just a quick, fast way to deal with normal distributions. And then when we start using formulas, we're going to get a little different numbers than what the empirical rule would tell us. But I think the empirical rule is just a way to do these real fast. So the empirical rule is memorize these numbers, 68, 95, 99.7 rule. Then I'll tell you what those mean in a minute for normal distributions. Okay, then read. This is the Algebra 2 notes. One type of probability distribution is normal distribution. By the way, you'd be amazed how many things in nature are normally distributed. This is why we are going to focus and hear the word normal distributions all the way till May. And as we go, you'll see what those are. I can't think off the top of my head. But a normal distribution is modeled by a bell-shaped curve called a normal curve, which we just talked about with percentages underneath, blah, 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 blah. Now, this is what I didn't like about the Algebra 2 book. They mixed X bar with the population standard deviation variable. Do you notice that? Do you see that? I think our book would contradict that. So X bar should go with S, mu should go with lowercase sigma. So I made the changes on the graph down here. But look, here's the 68, 95, 90, 9.7 rule. 68% of the data, if it's normally distributed, should fall within one deviation of the mean. That's one left and one right. So that is why they show over here 34% should be one to the right and 34 should be one to the left. 34 plus 34 equals 68, right? Okay, and then I'll tell you how you memorize this. We'll actually break it down like I did the other class. 95% of the data falls between two deviations of the mean. Well, how do I get this 13.5% then? I'll verbalize it. Then the next one we're going to actually do it. Take 95 minus 68, right? I want to get rid of this. Whoa. I want to get rid of this part to figure out what's left over on those wings. So I take 95 minus 68. This is simple math. This is not rocket science. I get 27, and then I have 27. Half of 27 is 13.5. 99.7% of the data falls within 3 deviations of the mean. What do I do to find the leftovers? Just take 99.7 minus 95, which is 4.7%. Divide that by 2, and I get 2.35% on these wings. Now, how do I get this last minute percent of 0.15%? Well, if 99.7% of the data falls within 3 deviations, that only leaves 0.3% after that. Take half of that, and you get 0.15%. That goes past 3 deviations of the mean. And then notice what I did here. I changed all those X bars to mu's, because I really think that should happen. The variables should coincide with each other. For those that didn't get what I just did there, well, this is, I mean, all the way through May. Just listen, I think. Normally distributed. Oh, adult IQs are normally distributed. It's been found. Okay, I'm going to try to do my normal distribution curve before I try to answer these questions. Did you read it? If you read it, what number goes right? Cha. Hundo. What number goes right? Cha. 115. You got it. What number goes right here? The standard deviation is 15. So one deviation to the right is add 15. Another deviation to the right is add 15. Another deviation to the right is add 15. Here's 3 deviations. And then go to the left. What number is this? 85. What number is this? 70, right? What number is this? Okay. Oh, that's Samuelus. Can't stand him. He always makes me try to memorize stuff. But I do remember this. Can't remember where I put in here, but I think I remember he said something about the 68, 95, 99.7 rule. Okay. So 68% of the data should fall. This is easy. That means 34 and 34 equals 68, and I have a calculator to help me out on that. So I'm actually just doing the same thing that we did the last one. As long as you memorize this, mathematically filling in these areas is going to be simple. And you can use your calculator to do this. 95% of the data falls from here to here. Well, what I have to do first is take 95 minus 68, not rocket science, get 27. That means 27% of the data are in these 2 areas. So I have to divide that by 2. That's 13.5, but now I'm going to make them decimals. So that's 95% of the data. And then for this, there's only 99.7 of the, not only, but what I'm saying for only is, I only have this much left. What? I only have this much left. The difference between 99.7 and 95 for the third deviation area. Then divide that by 2. All right. This becomes 2.35%, which is 0.235. Sorry for writing that real small, but we need to kind of write these in order to do our calculations over here. And then what do I have left? I only have 0.3%. When I divide that by 2, that is 0.15%. That means this is 0.0015. I'm changing this to 0.0015. What did I do? Did I do something wrong? Oh, that's 23. Holy crap, that's 20. What are you doing? I told you I never was good at math. I always hated math. I can't even get this eraser. This is stunning. Oh, son of a... All right. I already paid in the swear jar, so I'm okay. It's 0.0235, right? Thanks, Chief. Got my back, huh? Fist bump. Okay. Now we can answer this question. 70 to 115. What percent of the data, what percent of the men have an IQ between 70, and this is how it's going to work when we're using the empirical rule. It's going to work out perfectly. It's going to work out perfectly. Then later we're going to need some formulas when not. What do I do with those three numbers? Add them up. Add them up. You got to add them up. Add them up. Day after day. I get angry. Anyone know the song? Oh, you kids these days. Okay, more than 85. More than 85 is all of these, right? Is there something better I could do than more than 85? What would be something faster? 1 minus less than 85, right? Anyone? 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 Bueller. Right? Less than 130? Well, less than 130 is all this, right? All this that I'm coloring in blue, correct? Is there something better than that? 1 minus. I didn't make a mistake in the top one, did I? Right? More than 85. I think I made a mistake last hour. Oh well, no one said anything. I'll stop the video. Somebody said for more than 85, I could have done 50 plus 34. Correct. Okay, and then for this one, if you surveyed 1,500 adults, how many could you expect would have an IQ between 100 and 145? Between 100 and 145 is 0.34 plus 0.135 plus 0.0235. That percent added together times 1,500. This is what we could expect. Now, there's been a thing about how do I round, all the things that we've done this year. This one doesn't really matter. Remember, this is about how many people, and it's, statistics, so you'd be close, but it wouldn't be exact what would actually happen. So feel free to round mathematically. It's fine, and just say about. It's not really a big deal. Okay? All right. The only reason I have this last one, and I forgot to talk about number 1, so I will bore you with that. But, hey, look at these two examples. The means are equal, but the standard deviations are not. You notice that? Notice this curve. This curve is what? Much what compared to the other one? Higher! It's much higher because the data is more condensed. Remember we talked about that? The smaller the standard deviation, the more compact the data is. And remember, if I break this out into deviations like this is supposed to be 68% of the area of the curve. So that's why it's got to be a much higher curve to get that proportionally. Whereas this standard deviation is more spread out, so the curve is more smushed not as high because the data is more spread out. So when you look at these, we should be able to make those comparisons.
Pseudo sizes are
And then, you know, that like this back up to here. Okay, won't let me do it. I always love that. Okay, back up to here. Wouldn't you agree that if I were going to try to find the area under this curve, I could find the area of all these rectangles and come close, right? Right?
correct.
And add up all those areas? That's a calculus idea. Wouldn't you agree that if I had rectangles that were skinnier, the skinnier that, so let's do this. Let's do a curve. Would this be a good set of rectangles to find the area of this curve? Yes or no? Why? What do we have? Like, what does this show? Like, there's gaps. So if I were going to find the area of these rectangles, the area of these rectangles would be somewhat close to the area under the curve, but it would be much less, right? What if I took that same curve and I put rectangles like this? Hmm. Mm-hmm. Hmm. Mm-hmm. Hmm. I'm not going to keep doing this. Don't you agree that the smaller the rectangles are, the less open area there is, right? That there's a question in the book that describes that, and that's what calculus students do. You know, some sort of formula, not formula, but just I'm not going to get into it any further.